So for the first problem, in how many ways can we write the number 2024 as a sum of positive integers? In this problem, the order of summons, for example, 1000 plus 1024 is not the same as if reversed. So the order of summons matters to us. For this problem, we can just consider the problem of balls and walls. Like we have 2024 balls. And then the question of asking how many ways can we write it as a sum of positive integers is the same as if we put walls between the balls. So for this corresponds to 1, and this corresponds to 2. And let's say this corresponds to maybe 2020. And this is 1. And then we have it, the sum of it is 2024. So this is how we approach this problem. And there are, like, as you see, between two balls, there is one space. So there's in total 2023 spaces. And for each space, we can decide whether to put a wall there or not. So there's a choice of 2. We can choose either to put a wall or not to put a wall. So the answer is 2 to the power of 2023. Yeah, because there's 2023 spaces. So this is the answer for this problem. Okay. Well, if you have any questions, you can just stop me immediately. Okay, so for problem 2, in this question, the order of summons does not matter to us. So in question 1, the order matters to us. So we have to partition this many of balls into some parts. But for this question, the summons does not matter. The order does not matter to us. So we can't use the method as we use in question 1. So for this question, we can just let me let A and K to be the number of ways to write N as a sum of K positive integers. So you can see for the answer of this question, so A 2024 1, this is just 1. Since we are asking for in how many ways can we write the number 2024 for using only one number. So that one number is 2024. So the answer is 1.
So in how many ways can we write so as I said just then, we let A and K to be the number of ways that we can write the number N as the sum of K positive integers. So for example, A 2024 1 is just 1. Since we can only write 2024 using one number, then this number has to be 2024, right? So we have only one way to use one number to write the number 2024. So in the end, the answer to this question is just the sum of 2024 A J, right? So for 1 to 2024, we sum up the total value of each possibility. So we sum up the number of ways that we can write 2024 using one number and then using two number, and all the way up to we can use 2024 numbers to represent this. So the answer to this question is just this sum. But for this sum, it is actually in question 3. So let me do the question 3 first, and then for question 2, we can just use a recursive formula to calculate the sum. So for question 3, let ank to be the number of ways that we can write the number n as a sum of k positive integers, where the order of summons does not matter. So we have to find a recursive formula for ank. So for this one, we can consider two scenarios. The first one is that the smallest number that we can take, if you think of it, is 1, since this is the smallest positive integers that we can take. So 1. And if we take this 1, then our sum becomes n minus 1, right? Since we take this 1 as one of our summons, then the remaining sum is n minus 1. We have left k minus 1 summons, right? Since originally we can use the sum of k positive integers, and then now we have used one of them. So we have k minus 1 left. And this is the recursive formula for this for this scenario. And then for another scenario, that's the smallest summoned is not 1. So it is another number. Let me call it, oh, no, wait. So it is another number. So we can basically just, for example, let me give an example. 11 is plus 3 plus 2 plus 1 plus 1. So, oh, we have 1 here. So maybe 2 plus 2. So the smallest summon is not 1. So what can we do? We can just decrease every of this summoned by 1. And 1, 1. And now we minus 4, right? So we have 7. So this is so we can have this sum. So the remaining sum is just n minus k, right? Since we have 4 summons, and k is the number of summons. We have 4 summons, so we minus k times 1 from the sum. So this is the remaining sum that we have. And we still have to represent this remaining sum using k summons. So we still have 4 summons, right? So using k summons. And this is the recursive formula for this part. So in the end, this answer is just minus 1, k minus 1 plus, let me just, plus this one. So this is the answer to this question. So back to problem 2. The answer to problem 2 is just the sum of so the sum of a and k, where k is from 1 to 2024, and n is 2024. So we can just write a computer program for this part. And computer program I will give you in the solution. So yeah, this is question 2 and 3. Do you have any question by far? So you can see my screen, right? So yeah, hope you can see my screen. Okay, so to problem 4, let B be the number of ways of writing number n as a sum of positive integers between 1 and k. So this time we're not using k integers, but we're using the sum of positive integers at most k, since it's between 1 and k. And order does not matter, but we have to write a formula, recursive formula. So with this one, yeah, for this one, so let us first consider k as the largest integer that we can take, right? K is the largest integer. So if we take k into our summand, then what is the sum that we have left? So if we take k, then we have n minus k. The remaining sum is n minus k, right? Since we take k, then we still have to represent n minus k using the largest summand is still k, since the largest summand is k. So we still have to represent this sum using integers from 1 to k. So this is the first scenario. And then the second scenario is, what if the largest sum is not k? Then the largest sum is at most k minus 1 in this case. In this case, so we have to write this sum of n using the positive integers from 1 to k minus 1, right? Since now the largest summand we can take is k minus 1. So we have to represent n using positive integers from 1 to k minus 1. And this is when the largest summand is not k. And sum this two up, this is the recursive formula of b and k. And to see the connection to this of this problem 4, to problem 3, we have to consider a diagram called a Young diagram. So what is a Young diagram? So let me write the sum first. So 11 is 4 plus 3 plus 2 plus 1 plus 1. Then the Young diagram is just this. Two, 4, 3 plus 2 plus 1 plus 1. So actually I can just type. So this is 4, this is 3, this is 2, this is 1, this is 1. So this is the Young diagram. So we have this, we represent 11 using 5 summands, and there are 4, 3, 2, 1, 1. So we have 4 square at the top, and 3 and 2 and 1 and 1. So this is actually one of the representation of 11 using the largest summand is 4. So you can see this is actually one of the possibilities of B and K. So now if we imagine we can rotate this square, no, rotate this diagram. I rotate it. So if we rotate it, it now becomes becomes this, right? Consider it rotated anti-clockwise by 90 degrees. It becomes this, and we have here 1, 2, 3, 5, right? And this is only 4 summons. So it corresponds to we are representing 11 using just 4 summons. So this is just ANK, right? Because we define ANK as the number of ways to write 11 using only four using k integers. So we are using 4 integers. And here, this is the one of the possibilities of writing 11 using the largest, using the integers between 1 and 4. So this is one of the possibilities. And for every one of these configuration of squares, we can always transfer it into this, you can always rotate it by 90 degrees, and then we have this diagram. And you can see that since the number of rows here, we have 5. After we rotate it, the number of rows will become the largest summoned here in the original diagram. So for every possible configuration of this diagram here, there's a one-to-one correspondence to the diagram here. The diagram here. So you can see that if we sum all the possible configurations here, it becomes BNK, right? Since this is all the possible ways of writing, for example, 11 using the largest using the positive integers between 1 and 4. So this is BNK, and then it is equal to the sum of, let me call it B star, B star and K. So this is just every one of the possible configurations. So for example, this is one of the possible configuration and is B star, and then we can transform it into A. So every one of possible B star, we can transform it into A. So in the end, we can just write this A and K. So since they are the same. And so this is the relation between BNK and ANK. So this is the connection to the previous problem. Do you have any question? Okay. So let me continue. Consider an n to n by n grid. If we want to go from this point to this point and not crossing this y equals to n line, how many ways can we have it? So let's first consider, so if you think of it, the number of ways that we don't cross y equal x is the number of ways that is the total number of ways from this point, from the bottom left corner to the upper right corner, minus the ways, minus the number of paths that we cross this line, right? So the total number of ways minus the number of ways that we cross this line is the number of ways that we don't cross this line. So the total number of ways, you should know from the from last problem set, is just 2n choose n, right? Since we have totally 2n steps to take, and we can choose and there is 6 steps. So there's n steps that we're going right and n steps that we're going up. So we can choose just which 6 steps that we want to go right or go up. So it's 2n, choose n. This is the total number of ways. And then and then we want to calculate the number of ways that we cross this line, the total number of ways that we cross this line. So consider, for example, a random path that I go from here, here, into here. And then at some point, I cross this line. I not just touch it, I cross this line. And then just randomly go to the upper right corner. So consider this path. So we can consider the reflection of the path just after we cross this line. So we consider at the point P, we consider its reflection of the remaining path. So every up, we translate it to right, and every right, we translate it to up. So the reflection of the remaining path after P is just, so here we go up, we go right. And here we go right, we go up, we go right, we go up, right, up, up, we go right, and up, we go right. Where am I? And right, we go up, and up, we go right. So yeah, yes, here's the reflection. And we ended up at a point, this is 5, 7, right? So this is 5, 7. And actually, no matter how the path after this P, so no matter how the remaining path after P looks like, in the end, if we just reflect, we have the reflection of it, it will always end up at the point n-1, n-1 and n+1. So this is where we will always end up. So if we want to calculate the number of paths that we cross this line, it's just, since we will always end up here, the reflection will always end up here, and the reflection has a one-to-one correspondence with this one, this path, right? You can easily check that. Every possible path after P, we have exactly one possible path of its reflection. So there's a one-to-one correspondence. Then the reflection of the path that crossed the line will always go from 0, 0 to n-1, n+1. So we can calculate how many paths that, how many possible paths that we will reach here. So it is basically easy to calculate. It's just, so here we have n+1, here we have n-1. So in total, it's still 2n. But this time we're choosing n-1 or n+1. So we're choosing n+1 steps to go up, right? So this is just how many ways we can go from 0, 0 to n-1, n+1. So this is the number of ways that we cross the line y equal to x. And the total number of ways we minus the number of ways that we cross the line is the remaining answer. Is the answer to this question? Okay, okay. Then for question 6 is just trivial, right? Because I just calculate how many ways we're going from 0, 0 to n-1, n+1. And the question 6, problem 6 is asking, consider an n+1 times n-1 grid. We want to go from bottom left to the top right corner. So it's just 2n, choose n+1. Same as this one. Okay. And for this part, I think there's a mistake. I think it's we're asking for we're asking that so because I think there's a mistake where we don't have the same number of paths in problem 5 and problem 6. So yeah. So let me move to question 7, problem 7. in how many ways, in how many sequences of the opening brackets and closing brackets of length 2 times n are valid parenthesization sequences. So the definition of validity of parentheses are validity means that at every prefix we should have the number of opening brackets should be more than the number of closing brackets. So number of opening brackets so for example, at this prefix we have 2 opening brackets and 1 closing brackets, and we plus this one, they are equal. So it's not so the closing brackets is equal to the opening bracket. So this is a valid parenthesization. But if we have some points, the prefix in the prefix, we have less opening brackets than that of closing brackets, for example, just this one. So at this prefix, we have 3 closing brackets, but only 2 opening brackets. So this is not valid. Or maybe let me add one here. So you see that at this prefix, no, this is actually valid. Let me add one more here. So you see that at this prefix, no, this one. Wait a second. At this prefix, we have 3 closing brackets, but only 2 opening brackets. So this is also so we are already like invalid here. So this is an invalid parenthesization. So this is the definition of validity of the parenthesization. So at every position, the prefix should have more opening brackets than the closing brackets. And there's a hint that we can map this question to the question of problem 5. So maybe let me copy this. So let me copy this one. So at every so if you map every closing bracket to a right and every opening bracket to a up, so it corresponds to the number of paths that don't cross this y equal to x line, right? For example, if we take every actually it should be, I think this should be up and this should be right? Yeah, I think there's a mistake here. So we should map every closing bracket to up and opening bracket to right, or else at the beginning we'll just go up and cross the line. Okay, so let me map every closing bracket to up and opening brackets to right. So for this configuration, we have right, up, up. So we reach here. It already crosses the line. Excuse me. It already crosses the line y equals to x. So it's not a valid parenthesization. So this line actually governs that y equals to x, right? So it means that at this line, all the points at this line, we have equal number of opening brackets and closing brackets. So if we cross the lines further up, we go up, it means that we have one more, because up is closing brackets, it means that we have one more closing brackets than the opening brackets. So whenever we cross the line, it means that our parenthesization is not valid. So if we map closing brackets to up and opening brackets to right, our path should always stay below this, or we can touch it, but we should always touch or below this line. So this is the number of our valid parenthesization, and the answer is exactly this one. So the answer is still this one. Yeah. For question 8, 200 students took part in a competition, and the competition has 6 problems, and each problem was correctly solved by at least 120 students. So we have to prove that there are 2 students such that every problem is solved by at least one of them. So they cover the union of the problem sets that are solved by these 2 students should be all of the problem. So let's consider a bipartite graph. So on the left side we have students, on the right side we have problem, and if we connect one of the nodes on the left to another on the right, it means that this student has solved these problems. So you just randomly connect them. Yeah. And now, since we have 200 students, and each problem is solved by at least 120 students. So if you think the minimum, so if you think of the edge in the middle, so there's at least how many edge? Since every problem is solved by at least 120 students here, so every problem here should have at least 120 edges connected to the nodes on the left. So there's at least 6 times, and every problem has at least 120 edges. So there's only in total 720 edges in the graph. So since this is the minimum number of edges exists in the graph, and if we take, since we have 200 students and we have 720 edges, so if we distribute these 720 edges between these 200 students, you will see that actually ceiling. So this is 4, right? So what it means is that if we take every edge and we connect and we put this edge between one of the students on the left to one of the problem on the right, then there must be a student on the left that has 4 edges. Because if we only, so if you consider this, so let me just put the first node, we put 1 edge here, and the second node we put 1 edge here, and the third node we put 1 edge here. So after we put 1 edge in between the students and the edge for all the students, so there's 200 students, so there's 200 edges, and then we still have 520 edges left. So we still have to put for another round, and so on. So in the end, after we put 3 edges for each student, So this corresponds to only 600 edges, and we still have 120 edge left to put here. So there must be a student that has 4 edges connected to the problems. So we have found a student. Let me denote it as A. So we have found this student with at least 4 edges to the problems on the right. So the problem remaining now is to find another student that has 2 edges to these 2 questions, right? The questions that are not covered by A. So we have to find another student that has 2 edges to here. So how we're going to do this is that since these 2 questions are solved by at least each problem of them are solved by at least 120 students. So totally there should be 240 edges connecting from left to these 2 questions, right? So there's 240, 2 times 120 edges from left to right connecting to these 2 questions. And we only have 200 students. So these 2 edges must be distributed, these 240 edges must be distributed between these students. And we have more edges than the students here. So there's like 40 more. So we have to, so there's at least one of the students that has 2 edges connecting to these 2 problems. So there must exist one student that is like this, that solved these 2 problems. So we take these 2 students, A and B, they solve every problem. Okay, so do you understand this part? Okay, so let me go to the next problem. So an L-terminal consists of 3 squares connected to each other in the shape of an L. So it's like this. This is an L-terminal. And we have 2 to the power of n times 2 to the power of n grid of squares and have removed 1 square from it. So prove that the remaining shape can be covered by this. So I don't have the example. So we can prove this by induction. So let's consider the base case. The base case is when n equals to 0, it is 1 times 1 grid. So of course it cannot be covered. So we have to, the base case is when n equals to 1. So we prove this by induction. Base case equals to 1. N equals to 1, we have 2 times 2 grid, right? And we remove 1 square. It is exactly a L-terminal. So the base case we can have it. So the base case is correct. And then induction step, we have to assume that a 2 times 2 grid of square can be covered by L terminal after we remove 1 square from it. We have to prove that this is the same to the power of n plus 1 times 2 to the power of n plus 1 grid. So we have to prove this. So now let's look at the problem. So for n times 2 to the power of n times 2 to the power of n grid of square, it can be covered by L trinomial. We assume this. This is our induction hypothesis. And we prove that when n equals to n plus 1, we have to prove that it is also the same. So we can prove by induction. Let me draw a square. So 5, 6. Whatever. Actually, it's not a square, but whatever. So consider this as a square. And it has length 2 to the power of n plus 1. So we can divide it into 4 parts. So now consider this one. Yeah. Just imagine that these 4 parts are equal. So consider this as 4 equal parts. So each of them will have 2 to the power of n, length 2 to the power of n, right? So now we have to remove 1 square from this grid. So let's remove it anywhere. We can remove it anywhere. So let's assume that it is here. So we remove this one. And by the induction hypothesis, this is an n2 plus 2n times 2n grid. By the induction hypothesis, we can cover it by L trinomial after we remove 1 square from it. So we can cover this one. And for the remaining 3 parts, we can just put an L trinomial square here, L trinomial here. So if we put it like this, so this is an L trinomial. So for the 4 parts, for all of the 4 parts, we have 1 square removed now. So we already covered it by L trinomial, so we can consider it as removed. So each part now is, so this is a 2m times 2n grid, and this is also a 2n times 2n grid, and this is also a 2n times 2n grid. So by the induction hypothesis, we can also cover these 3 parts using L trinomial. So in the end, we can cover the entire grid using L trinomial. So this is the proof. So we prove that for 2n plus 1 and n plus 1 grid, it is the same. So we can also cover it. And so we actually proved that we proved this. So for any n, we can actually cover it by L trinomial if we remove 1 square from it. So now let's move to problem 10. So there are 6 candidates for president, and every pair of them are either friends or enemies. So we have to prove that 3 candidates are all friends to each other, or they're all enemies to each other. So there's a mutual relationship between a pair of candidates, and it is either friend or enemy. So actually, their relationships represent a complete graph, right? So for every node represents a candidate, it has 5 edges between other 5 candidates because he is either a friend to the other 5 candidates or an enemy to the other 5 candidates. So this is a complete graph. Every node has an edge to every other node. And by the pigeonhole principle, so we have 5 edges going out. By the pigeonhole principle, there has to be 3 edge of the same color. Why is that? Because let's assume that we want to keep our edges below 3. So I want to first color this as green, and then I will want to color this as red, I color this by green, and then I color this by red. So now we have two green edges and two red edges. But for this one, no matter how we colored it, so we can only color it as green or yellow. No matter how we color it, so if I color it as green, we have three green edges. And if I color it as red, we have three red edges. So there must be three edges from a node that has the same color. So let me now just remove these two edges. So let's consider this candidate, and candidate A. It has three edges going out, and let's call the other three B, C, and D. We have three edges going out, and the way we prove this is that since we have let's call green is friend, and red is enemy. Okay, so A is already a friend with B, C, and D. And if B and D, they're also friend, we have a green cycle, right? So this is a group of three candidates that is all friends. We have green, so we cannot put green here. We can only put red here. So if we want to, we don't want any group of three that is all friends or all enemies. So we cannot put a green here. So if we put a green here, A, B, and D, there are three friends. So we have to put a red here. And consider A, B, and C. It is the same case because AB is already friend and AC is already friend, so BC cannot be friend. So we still have to put a red edge here. So there BC should be enemy. And the same case for A, D, and C. We should always put a red here. But now, if we look at the graph, we have a group of enemies of group of size 3. Right? If you see B, C, and D, they are a group of enemies. So in the end, we will always have a group of 3 that is all friends or all enemies.